Okay, so in this video we're going to continue looking at section 4.3, and our goal is to talk about the first derivative test. Which tells us whether or not a critical number is a local max, a local min, or neither. Okay, and in our last video, the key connection that we made between a function and its derivative is that if a derivative is positive, then the function is increasing. And on the other hand, if a derivative is negative, then the function is decreasing. Okay, and this gives us the information that we need for the first derivative test. What the first derivative test says is that suppose that I have a function f with a critical number at x equal to c. So suppose f is a differentiable function. That's just because we're going to need to look at the derivative. So we have to be able to take the derivative. And suppose x equal to a number c is a critical number for the function f. Okay, then there are three things that could happen. So case 1, if the derivative is positive, to the left of c, so for x less than c, and it's negative to the right, so for x greater than c, then the function must have a local maximum at c. Okay, and we're going to have two more cases, like I said, and if you try to memorize positive left, negative right, this is going to be a mess. But if you draw a picture, it's really not that hard. So the picture that goes with this case, let's see, here's my graph. I know I have a critical number at c, so let's say it looks like that. If it's positive to the left, that means to the left of c, so over here, my function is increasing. Well, if it's going to increase and go through c, it's got to look something like that. And negative on the right means that on the other side my function's going to decrease. Well, if I go from increasing to decreasing, then I have to have a maximum there where I switch. That's all this is saying. Okay, the second case that could happen is the opposite of this. So if I start out decreasing, meaning that my derivative is negative to the left, and it's positive on the right, then the function has to have a local minimum. At x equal to c. And again, if you try to memorize this rule, it's going to be hard. It's easier to draw a picture. So for this one, I've got a critical number at c. I have some function value that goes with it. And negative to the left means that to the left of this point at c, my function is decreasing, so it's got a downward slope. So it looks something like this. Positive to the right means that it's increasing to the right, and if I have that behavior, then I've got to hit bottom somewhere in between somewhere in between the decreasing and increasing, so I'm going to have a minimum. Okay, and the last case, the only possibility that's left is that it's either negative on both sides of c or it's positive on both sides of c. So if the derivative doesn't change sign at c, it's not a maximum or a minimum. So if f prime of x is positive on both sides of x equal to c, or if it's negative on both sides then I don't have a max or a min at the c. We called that a plateau. Then there's a plateau, then there's a plateau at x equal to c. Not a local max or a local min. And again, let's look at the pictures that go with this. If my function is positive on both sides, then let's say here's my c and here's my function value. See, what that means is that on both sides my function is increasing. So to the left it's got to look something like this. It does have to flatten out because if c is a critical number, my derivative there has to be 0. So it flattens out at c, but it flattens out and then it continues increasing on the other side if it's positive on both sides. And of course the other option is maybe it's negative on both sides. And if that's the case, we sort of just flip this. So if I have a critical number at c but it's negative on both sides, then it's going to be decreasing on both sides, which means it looks like this. Okay, let's look at an example where we use this first derivative test. Let's use a trig example. Let's find all local max and min for the function g of x equal to x plus 2 sine of x between 0 and 4 pi. Okay, and before I get started, I want to emphasize how this is different from the examples that we saw in section 4.1. Even though I'm given these two endpoints, I'm looking at a specific restricted domain, this is different from 4.1 in two ways. Which you might not catch if you're just reading these notes. The first is that for this one, I want to find the local max and min. But in 4.1, the method we talked about found only the absolute max and min. So this is going to be different. The method from 4.1 got me two numbers. It got me the absolute maximum and the absolute minimum. Going in, I don't know how many local maximum and local minimum I'm going to find. It could be 0, or it could be a lot more than 2. So there's a big difference between local max and min and finding the absolute max and min. The other difference, which isn't really highlighted here, is that this is on an open interval. I don't want to include 0 and 4 pi unless for if they're actually local max and min if I zoom out a bit. So maybe I'll say that I don't want to include 0 and 4 pi unless they actually are critical numbers. Whereas in section 4.1, those endpoints were sort of given special treatment because I cut off my graph at those points, and if that point happened to be a bigger number than the rest of the ones near it, it became an absolute max, even if it wasn't a critical number to start with. Okay, so how are we going to answer this question? We're going to start by finding the critical numbers. So our function was g of x equal to x plus 2 sine of x its derivative then is 1 plus 2 cosine of x. This is defined everywhere because I can take the cosine of any angle. So to find the critical numbers, I want to know where is it equal to 0. That means that I want to know where is cosine of x equal to -1/2. So pull out your unit circle and tell me what angles you can find where cosine is equal to -1/2. Okay, you should get two angles from your unit circle where this happens. This happens at the angle 2 pi over 3 and the angle 4 pi over 3. Maybe I should emphasize here, when we have an equation like this, we're not going to use the arc cosine. So we introduced the arc cosine in chapter 3, but the arc cosine of this would just give me one angle where the cosine is -1/2, and I want all the angles. So don't use arc cosine of -1/2. That would give us one answer. But we want all of them. Okay, and we're not done yet. We found two angles on the unit circle where this happens. But if I go back, I wasn't looking at angles on the unit circle. I wasn't restricted between 0 and 2 pi. I wanted all the angles from 0 to 4 pi. So we have to go around the unit circle again and add a couple more angles. So maybe let me sketch the unit circle over here. We found 2 pi over 3 and 4 pi over 3, something like that. If I go around the unit circle, that gets me to 2 pi, and I want to keep going. So if I go around again, this 2 pi over 3, the second time around, I add 2 pi, and that becomes 8 pi over 3 on the second pass. That's because 2 pi plus 2 pi over 3, this is 6 pi over 3, so that gets me 8 pi over 3. And on the second pass, that 4 pi over 3 becomes a 10 pi over 3. Again, because if I add 2 pi to 4 pi over 3, that's how I get 10 pi over 3. So what I have at this point is I have 4 critical numbers that I'm going to use, and now I'm going to use the first derivative test to figure out which of those are local max and which are local min. Okay, and that's actually exactly the same process we used to figure out where a function was increasing and decreasing. We know where the derivative is 0, and we need to figure out where it's positive and where it's negative. So let's draw our number line. Our number line is going to go from 0 to 4 pi. Those are the angles that we're interested in. And we had 4 places where the derivative was 0. We had 2 pi over 3. We had 4 pi over 3. We had 8 pi over 3. And we had 10 pi over 3. Okay, so when I split up my number line at those 4 places, it gives me 1, 2, 3, 4, 5 intervals to consider. And let me remind you, the derivative that we got, g prime of x, was 1 plus 2 cosine of x. Okay, so I'm going to take one number from each of these 5 intervals. I'm stopping at 0 and 4 pi. So each of those 5 intervals, and I'm going to plug them into my derivative to see if I get a positive answer or a negative answer. Okay, let's maybe do the obvious ones first. I can plug in pi. When I plug in pi, what do I get? Well, the cosine of pi is -1, so I get 1 plus 2 times -1, which is -1. And I don't care so much about the 1, I care that it's negative. So between 2 pi and 4 pi, my function is decreasing. Let's try 2 pi next. G prime of 2 pi is 1 plus 2 cosine of 2 pi. What's the cosine of 2 pi? Cosine of 2 pi is 1, so I get 1 plus 2 times 1, which gives me a positive 3. Again, I don't care so much about the 3, I care that it's positive. So that tells me that on this interval, my derivative is positive. And already at this point I can tell that 4 pi over 3, if it was decreasing and then increasing, what does the first derivative test tell me? Is that a local min or a local max? It's a local min. If I go from decreasing to increasing, my graph looks like this. So I have to have a minimum in there. Okay, let's keep going. Let's see what happens at 3 pi. When I plug in 3 pi, I get 1 plus 2 times cosine of 3 pi. Well, 3 pi is the same place on the unit circle as pi, so it's got the same cosine, which is -1. So I end up getting a negative answer. And that tells me, what does that tell me about 8 pi over 3? It tells me that 8 pi over 3 is a local max because my derivative went from positive to negative, so I went from increasing to decreasing, so it's got to look like this. Okay, and now I need to get a little bit more creative because I need to also test some numbers between 0 and 2 pi over 3 and a number between 10 pi over 3 and 4 pi. So for an angle between 0 and 2 pi over 3, maybe a natural choice is pi over 3. If I plug in pi over 3, I get 1 plus 2 cosine of pi over 3. And cosine of pi over 3, look at your unit circle, it's the square root of 3 over 2. So I get 1 plus the square root of 3, and I don't need to know what that is exactly. What I need to know is that that's positive. So for angles between 0 and 2 pi over 3, my derivative is positive. What does that tell me about 2 pi over 3? Is 2 pi over 3 a local min or a local max? Well, if I go from increasing to decreasing, that's going to be a local max. Okay, and one more. I need to test something between 10 pi over 3 and 4 pi, so maybe 11 pi over 3 is the natural choice. That's going to be 1 plus 2 cosine of 11 pi over 3. Okay, and now I can't tell you to just look at your unit circle because 11 pi over 3 isn't on your circle, but we can find the equivalent angle on your unit circle by subtracting 2 pi. So 11 pi over 3 minus 2 pi, which is 6 pi over 3, is 5 pi over 3. So 11 pi over 3 will have the same sign and the same cosine as 5 pi over 3. So g prime of 11 pi over 3 is 1 plus 2 cosine of 5 pi over 3. And now I can tell you to just find that angle on your unit circle to find its cosine. The cosine of 5 pi over 3 is the square root of 3 over 2 again. So I get 1 plus 2 times the square root of 3 over 2. It's 1 plus the square root of 3. And again, I don't care so much about what that is. I care that it's positive. So in between 10 pi over 3 and 4 pi, my function is increasing, which tells me that 10 pi over 3 is a local min. Okay, and now we want to go back and answer the question. The question didn't ask where these local max and min happened, they asked what they were. So because I'm looking for the local max and min values, I'm looking for y values. So I need to find the y values that go with these critical numbers. So for this third step, the way that the question was posed is important. The question asked me to find the local maximums and the local minimums, which means that I'm looking for y values. If it had asked me to find where the local maximums and where the local minimums had happened, I'd be looking for x values and I'd be done. But to find the corresponding y values, we just plug them in. So let's see, we said that we had a local max at 2 pi over 3. The corresponding y value is what I get when I plug in that to the original function. So g of 2 pi over 3 is 2 pi over 3 plus 2 times sine of 2 pi over 3. Remember, the original function was g of x is equal to x plus 2 sine of x. So I'm just plugging these in there to get the y values. And I don't know how much we want to simplify that. Maybe we'll just write out the sine of 2 pi over 3 is the square root of 3 over 2. So this comes out to 2 pi over 3 plus the square root of 3. And we'll just stop there. That's one of our local max. The other local max happens at, let's see, where did it happen? It happened at 8 pi over 3. So we plug that into our original function to find the y value. I get 8 pi over 3 plus 2 sine of 8 pi over 3. 8 pi over 3 has the same sine value that 2 pi over 3 does, so this becomes 8 pi over 3 plus the square root of 3. And we also had two local min values. I had a local min at, let's see, first one was at 4 pi over 3. So the y value that goes with that, I plug in 4 pi over 3 to my function. I get 4 pi over 3 plus 2 sine of 4 pi over 3. The sine of 4 pi over 3 is negative square root of 3 over 2. So I get, when I multiply by 2, I get a negative square root of 3. Okay, and I also had a local min at 10 pi over 3. So let's plug that in. G of 10 pi over 3 is 10 pi over 3 plus 2 sine of 10 pi over 3. The sine of 10 pi over 3 is the same as the sine of 4 pi over 3, so I end up getting this negative square root of 3 again, so I get 10 pi over 3 minus the square root of 3. Okay, so I have two local max values, and I have two local min values. We're almost done. I mean, that is our answer, but I want to give you the picture that goes with this because I think it's helpful. So let's go over to Desmos and look at the graph of this function. If I graph y equal to x plus 2 sine of x, this is the shape that I get. I was looking at x values between 0 and 4 pi, so that's between 0 and 4 pi is about 12, so about here. And what I found is that I have two local max, one happens here and one happens there, and I have two local min, one here and one here. So those are the x and y values that I found using the method that we just used. Okay, I'm going to stop there. In the next video, we'll look at one more example like this, and then we'll be done for today.